All right, welcome back YouTube to another LeetCode challenge today. We are going to be doing algorithms. We're going to just warm up again with some easy and something that I haven't done before. If you saw the last video, I struggled with it. And so, let's just do another easy one here. And we're going to pick one. Let's see. Oh, okay, we've got a binary tree problem here. Interesting. I like binary tree problems. So this problem is called binary tree post-order traversal. Okay, given the root of a binary tree, return the post-order traversal of its nodes' values. Okay, so this is just a classic post-order traversal. Let's see here. And we're representing our binary trees as a list of values. Okay. And the output, of course, is in post-order traversal. So what is post-order traversal? If you are traversing a binary tree in depth-first search, that is going basically top to bottom instead of left to right, layer by layer. Depth-first traversal has three types of traversals: pre-order, in-order, order, and post-order. And post-order is left, right, root. Okay, so what that means, and let's just go to a note here, is that if we have a tree, let me see if I can draw this out. I haven't done one of these in a notepad in a while. Just do like 3. Move these over a little bit. Three, 4, 5, 6, 7. Okay, so if we have a tree that's just a classic 3 layers, 1, 2, 3, 4, 5, 6, 7 nodes, the post-order traversal of this binary tree is going to go 4, 5, 2, 6, 7, 3, 1. So we're going all the way down to the left first, right? So let's get a new line here. Post order traversal is equal to left, right, and then root. So go all the way down to the left. And by the way, the children of these leaf nodes are none. So I'm not going to write out none representing them. So we go down to the very bottom and it's left, and we go right, and then we go root, and we have done the left side of the tree. And we go down to the right and we go left, right, root, and then finish up with root. So 4, 5, 2, 6, 7, 3, 1. And let's just confirm that. Let me make sure I'm not doing, okay. Oops, I adjusted the window too far. Give me a second. There we go. There we go. Okay, I'll stop messing around with the window sizes here. Let's see here. So case number 5, we are going to go, I think it's just 1, 2, 3. I think this is representing this in order traversal. So 1, 2, 3, 4, not in order. 5, 6, 7. Layer order traversal. So breadth first search. Okay. And output is going to be a list. So let's just return a list of one number. Okay. 4, 5, 2, 6, 7, 3, 1. 4, 5, 2, 6, 7, 3, 1. Okay, perfect. So we have a solid understanding of what the problem is expecting of us. Okay, classic depth first traversal here. And we are going to be building up a list. So let's make another parameter for a list. And we're going to call it, we're going to call this values. And it's going to have a default value of none. And the reason why we want to have a default value of none as opposed to an empty list is because you do not want to have mutable values assigned as default values. Python is assignment by, sorry, how do I word that? Assigned by value, assigned by reference. It's if you have a mutable value assigned, it'll keep modifying the same list. And while we might not have problems in this particular LeetCode example, it can cause some really unexpected behavior when you have a method or function that keeps modifying the same list, and you wonder like where all these values are coming from. It's because Python is modifying the exact same list in memory. So we want to call it none, and then if values is none, values is going to be an empty list. Okay, then we are going to have our base case. If root.value is none, we're going to return. And this is so that we don't recurse forever. If it's not none, then let's see here. We are going to go left, we go right, and then we go root. So left, to traverse left, we go Postorder traversal on root.left. If we want to go right, we call the same function, same method on root.right. Let me make this a little bit more clear. We traverse left, we traverse right, and then we perform an operation on root. What is the operation that we are performing? Well, in this case, it is simply appending the value to our values list. So in this case, values.append root.val. Okie dokie. So that's going to go through our entire tree and append the values to the list. And then we need to make sure, I accidentally hit back there. Let's try that again. Okay, I'm glad that the code stayed. Okay, now we need to have our return of the list. Okay, so in that case, eventually we will get back to the root. We will append 1 to the list, and then we want to return it. So we are going to return values. Figuring out where to put the return statement in any kind of recursive problem is kind of challenging. And if we have time here, I'll do a visualization of the stack in memory just to make sure that it's performing how we expect it to. So return values. Okay. And let me just check my work here. I think that is about it. Okay, values initially starts off as none. Okay, so let's do our walkthrough here, or step through here. We're going to call this our stack. How to do this in text? We'll just call this the bottom of our stack. Okay, so we invoke Postorder Traversal on our root that has 1 inside of it. 1 gets added to the stack, pushed to the stack. Then values is none, so values becomes this empty list. We're going to call this values, which is an empty list. Root.val is none. Root.val is 1, so it is not none. And by the way, this is the node with 1 inside of it. So maybe I'll put this in brackets here, just to represent that this is a node. It does look like a list. Normally, I'd like to draw a circle around it. This will do for now. So then we're going to call Postorder Traversal on root.left. Root.left is the node with 2 in it. So the node with 2 gets pushed to the stack. And values is not none. Root.value is not none. 2's left gets pushed to the stack. 4. Let's see. Values is not none. Root.value is not none because it's still 4. So now we are going to traverse left and push root.left, which is none, to the stack. Okay. Then let's see here. When we get to none, values is not none, root.value is none. Okay, so that's incorrect. We need to make this if root is none, because there isn't going to be a node whose value is none. This is just a none type object. So this is our base case. So we're going to return. So we pop none off the stack. We return to the 4, which is still on the stack, and we push the 4's right onto the stack, which is none. We go through a very similar process where if it's none, it returns early. That's the base case. We are purposefully not pushing none to our list of values. Okay. So now we are still at 4. We have traversed left and we have traversed right. Now we are going to perform our operation, which is appending the value to values. So we push 4 to the values list. Perfect. Okay. 4 is now complete. It returns values to the node, the method invoked on node with number 2. However, we're not doing anything with the return value after we traverse. So it 4 pops off the stack. This has, when we are looking at node number 2, traversing left has returned a list with 4 inside of it, but we're not doing anything with it. Okay. Ooh, actually, and of course, if we are going to be traversing left and right, we need to be passing in values. Oh, I am rusty today. Yeah. Since we added this this list called values as another parameter to our method, we of course need to make sure that that gets passed into the recursive calls. Okay, this is how it updates and basically changes over time. And it's not going to be none because we have created the list there on 10, or we have modified it. Okay, so let's see here. So then when we traverse right, we are going to be passing. Okay, so let's see here. Traversing left. Postorder traversal passing in values. Do we need to assign this to a variable? Do we need to assign this to values? Postorder traversal has modified values. We pass in an empty list, returns a list with 4 inside of it. I think we do. I think we need to reassign values. Because this updated values gets passed into the right traversal. Yeah. So we do, okay, yeah. This is going to return the subtrees post order traversal. Then we assign it to values, reassign it to values again so that when we go to the right, those values get added, and then we do the root. Okay, so when we traverse to the right of node with number 2 in it, we are passing in the list with the number 4 to the right. Okay, so 2's right is 5. Then when we go on the node with 5 inside of it, we run post-order traversal on 5's left, which is none. We kind of go through this same song and dance here, where none gets pushed to the stack and then popped from the stack. And then 5's right, which is none, gets pushed to the stack and popped from the stack. And then finally, 5 gets appended to values. So values 5, okay. And then finally, so the list with 4 and 5 gets assigned to values. 5 gets pushed, popped from the stack. Values, we append the node with 2 inside of it. So root.value is 2. Okay, so we're going to append 2. And then this is going to return up to the node with 1 inside of it. Okay, yeah. So the node with 1 its left traversal returns 452, and we assign that to values. And basically we go through the same process on the right there. And for the sake of time, I'm not going to go through the whole right side of the tree. Let's see if this works. Uh-oh. Post-order traversal is not defined. Oh, of course. Yeah, this is a method here. Self.postorder traversal. Runtime error. Values.append root.val. None type object has no attribute append. Okay, values should be when we get to our base case, it's still returning. This is returning nothing. We want it to return values. Okay, so basically what was going on there is when we were getting to the leaf nodes and their children are none, we were hitting the base case and it's returning none up to the parent. What we want instead is to return the current state of values. Okay. Now we've got an accepted case. There we go. Cool. And let's submit. Hey, there we go. So, good runtime. Not super memory efficient. Let's see, in terms of runtime, this is going to be O of n, because n being the number of nodes inside of the binary tree. In this case, just appending to a list at every single node, that's O of 1. So we do an O of 1 operation n number of times. And then in terms of memory, it's actually going to be the height of the tree. And the height of the tree represents the maximum number of nodes in the stack. And the stack, of course, is in memory. So the higher the tree, the more layers there are, the more values, the more nodes that are going to be inside of the stack. So that's going to be O of H. Okay. Actually, I'm interested to see what it says here for space complexity. O of n. That's kind of true. It's O of n if the space is O of n if it is a completely unbalanced tree. If you imagine a tree who only goes to the left and therefore the number of nodes represents the height of the tree, so it's not even in a tree shape, it's basically a linked list at that point, and then potentially the entire tree will be in memory. So O of n, yes, kind of. If it's a balanced tree, it's going to be O of H. And the number of layers in a balanced tree, there's a formula for that I'm blanking on. O of log, I think it's O of log n. Log base 2. Yeah, because every new layer doubles the number of nodes. Okay. But that would assume that the tree is balanced. Okay, so this is a perfectly working solution. What's the other way to do it? So this pattern where we create a new parameter called values, and it represents kind of the running list as we traverse the tree. This is called like an accumulator pattern. when you're doing a recursive solution here, and values is the accumulator. It accumulates values as you traverse. The other major pattern that you can use is called a helper function. And the idea with a helper function, and it feels bad to delete all of this good work, but we already got an accepted answer. It doesn't really matter here, is we are going to write a function that traverses the tree. And it's going to be a function inside of this post-order traversal method. And then at the bottom of this post-order traversal method, we invoke the function on the root. It traverses the tree, and then it builds up this list that we are going to call values. And it is going to be a variable local to the method post-order traversal, which is an enclosing variable from the perspective of the traversal function. So we're going to call this def traverse, and it is going to take in a root. Does it need anything else? I don't think so. Let's see here. And the idea is traverse actually isn't going to return anything. So what we're going to say is if root traverse root dot left traverse root dot right, and then values dot append root dot value. I'm pretty sure this will work if I don't non-local values, but I think this is better code when you make it explicitly clear that values is a variable that is not local to traverse. It is an enclosing variable. And if you look at the order of where Python looks for variables, the acronym is LEGB, local, enclosing, global, and built-in. So it'll check locally first, then it'll check the enclosing, it'll check global, so any variable is defined outside of the class, and then it'll check inside of the built-in, so that like all the built-in variables, frankly, in this case, or built-in variables or functions. Okay, so from here we simply invoke traverse on root. Traverse goes through the entire tree, builds up values, and then we return values. Okay, perfect. I'm interested to see if it makes a difference if I non-local this or not. I think this will work because we're not creating a new variable. Yeah. I still think it's better code to do this, so I'm going to keep it in. Okay, interesting. I don't put too much stock in the fact that the last accumulator pattern had a quote-unquote faster runtime. This is still O of n, so it's still the same big O. And we're creating a new list here. Actually, that's why the last solution, the memory is also O of n, of course, because we are creating a list and its size is correlated to the number of nodes. Okay, so And of course, O of n is bigger than O of h height or O of log n. So it's always going to be O of n for both of them. In this case, with the helper function pattern, values, the size of values is going to be the number of nodes. And then we return values. Okay. So that is, which problem is this? The binary tree post-order traversal. Number 145, binary tree post-order traversal. That was a quick one today, and I showed you how to do it in 2 different ways. Recursive solutions really can be done with an accumulator pattern or a helper function. I generally prefer doing a helper function just because it makes more sense in my brain. I don't have to worry about a return statement inside of the traversing function. I can take advantage of the fact that values is defined outside as opposed to defining values as a parameter, an accumulator. But to each their own. So that'll wrap it up for today. Have a good one.